All right, let's get started. Just a quick recap of what we have on Monday, where we talk about exhaustive search, or we call brute force. So the idea of exhaustive search is that you lay down all the possibilities of what you want to search for, where you want to search, and for each of them, you try out if it's what you want. Okay, so this is the idea of brute force. You try all of them. So you first identify the search space. What is it that you want to search? Where is it located in? What are the possibility of these things that you want to search for? Identify the property of the element you want to search for, and then identify the output once the element is found, and the output if the element doesn't exist in that search space. That's the blueprint of brute force or exhaustive search, where we lay down all the possibilities. For each of them, we check if this is what we are searching for. If it's not, we go to the next element. If it's not, we go to the next element until you found one. Once you found, what is the output? Do you still continue or do you stop? So that's what we have been discussing on Monday based on different examples. So for example, if you are searching for an element and you are satisfied when you found one, then you can stop. You just do break once you found it. But if you are doing counting, it's also kind of a searching. You want to count a particular element, you need to search for it first. But when you search for it, you don't break because you want to continue to search for if there is any other element that is equal to the particular target that you want, then you don't have the break statement. You continue to count, okay? And another example is to identify the indices of all occurrence of the element of X. So if you want to know where are the positions of this element X in a list, again, you have to search for it. So we always use the same blueprints of identify the search space and what is the property you want to search for. And if you found it, what do you do? If not, what do you do? Okay. And then we come to this example of checking duplicates. Now, this is an example where we actually don't know the exact element that what we want to search, but we know the property of the element that we want to search. Okay. So basically you are given a list. All right. You will output true if it has duplicated value. That means a value that is non-unique, that it appears more than once, and you output false otherwise. Now, we don't know what elements are available in a list, so we don't know the exact elements of what we want to search for. Are we searching for one? Are we searching for two? And so on. We don't know exact element, exact number, or exact value that we want to search for, but we know the property of what we want to search for. If it occurs more than one, that's the property. Okay, so there are multiple versions that we're going to analyze. And the first version is what we have seen on Monday, is that we are looking at a list with special properties. Okay, this list has 500 integers, and each integer is randomly chosen in this range here from 0 to 9,999 inclusive. Okay, so if they exceed the duplicate value, which means a value that is non-unique, then the possibility has to be one of these values here. So basically, we're going to search for one of these values to see whether it occurs more than once in the list. We use the property of duplicates to help us to identify which one is, whether a duplicate could exist, okay? So that's the idea. So my search space now is this from 0 to 9,999, which is the same as range in Python 0 to 10,000, because these would generate integers starting from 0 to 9,099, not inclusive of 10,000, okay? And then for each of them, we check if it occurs more than once. If it is, then we found. So we can exit, we will break, okay? If at the end of the search, you try all the possibilities from 0 to 9,099, and none of them occur more than once, then you display the message that there is no duplicate, all right? So let's see. Here's an example. This is a list of random integers, 500 random integers. And this is how we're going to do it. So for each of the element in here, if you count the value for count the elements in this list is more than one, then you already found it. You just say that as duplicate equals to true, you print out the value or the element that it's occur more than once. and then you stop. You don't look for subsequent values anymore. And if it does not have any duplicate, that means has duplicates, it stays as false. It means every value that you have encountered so far only occur once. Then you say that all elements in L are unique. Okay, now we can generalize this further. Say we want to count how many non-unique values. Okay, so here it says that 224 occur more than once in the list. Could there be another value that occur more than once in the list? So we don't want to know these numbers, but for example, we just want to count how many of these non-unique values exist. Again, the same thing, we use the same blueprint, okay? Except we make a little change, all right? Instead of setting has duplicate equals to false, we create a variable called count and initialize a 0, okay? And everything stays the same except here, all right? We, instead of has duplicate equals to true now, I'm gonna add 1 to count because we want to count how many such elements occur, okay? And I don't break because I'm gonna continue to look for another duplicate if it exists, okay? Now, if count equals to 0, that means all elements in L are unique. Otherwise, we print count that will represent the number of non-unique elements in the list itself. You say that there are 10 elements in the list that are non-unique, okay? If you just look at this list yourself, this has 500 integers. It's very difficult to identify these 10 non-unique elements. So writing an algorithm to solve this problem becomes very essential. It's really difficult to know which one of these are non-unique because they are just too much to look manually, okay? Now, these versions require us to search for 10,000 elements, okay? From 0 to 9,099. So the number of iterations is 10,000, okay? And it's not, this doesn't mean that it just only run 10,000 computational steps. Each iteration costs you a step, but it's just not one step because at each iteration, you also execute this method here called L.count. And each of these executions, there are 10,000 executions of this. Each of these execution will incur some computational step. When you do .count, okay, behind the scenes, it has to go through the list to count how many times this value occur. Okay, so if you remember when we do count ourselves, we create our own algorithm to count, we actually go to the list. Every single time we count a particular element in the list, we go through the list once, every element in the list once, okay? So in the end, when we look at here, so we execute 10,000 in our for loop here, we have 10,000 iterations. It's repeat line 3, 4, line 3 and 4 10,000 times. In particular, L.count is repeated 10,000 times. Okay, each of these times, okay, so in L.count, okay, it might go through the list once, okay, go through every element in the list once. So in basically, we'll check every element in the list to see whether it is the element that you want to count, okay? So it will go through every element in the list once. So when you go through every element in the list one, you go to each list and you take one element and see whether this is what you want to count. Is this the one that you're looking for and you want to add one to the count based on the value? You actually occur a computational step, okay? So how many times elements in the list is examined in the worst case? So for each of these 10,000 rounds, okay, you incur L.count, and each of the L.count will go through every element in the list once, okay? So basically, for each of the 10,000 iterations, so you examined each element in the list once, okay? In the worst case, all right, because once you found it, actually in the worst case, yes, you examine each element in the list once. So there are 500 elements in the list. Okay, so for each of these iterations, you examine 500 elements. Okay, so in other words, for each of the 10,000 iterations, you examined 500 elements. Okay, so for each of the iterations, you go through the list. The list has 500 elements. The second iteration, you go through the same list again, and this list again contains 500 elements. And then the third iteration, you go through the same list again, which contains 500 elements. So in total, okay, you examined 10,000 times 500 elements. Okay, and examined this number of times of elements will incur this number of times of computational course, computational step. Okay, so roughly speaking, these incur 510,000 computational steps. So these algorithms of version 1 incur this number of computational steps. So each computational step involves going into the list and examining one element in the list. Okay, so there are 10,000 iterations. Each of them will incur L.count, which require you to check the list. The list contains 500 elements. So each of them will check 500 elements. So in total, you check this number of elements in your whole computations. So this is your computational step, roughly speaking. Okay, now this is pretty bad for us. That means in order to find duplicates, you need to run this number of computational steps. Behind the scenes, these are all the computational steps that is being taken off, which is about 5 million. All right, just to check whether it's duplicate of 500 elements, okay, we are basically running 5 million computational steps. So question is, can we shorten this? Can we optimize this? Can we not check so many times? Because if you have seen here, for each of the iterations, you examine the same list again and again for 10,000 times. All right, do we really have to examine this list 10,000 times again and again? Why do we have to do that? Can we not do that? So that's the idea of version 2. Can we not checking the same list again and again? So the idea is that, again, if you don't want to check the list again and again, you just want to go through the list once, okay? Then how do we determine whether the number that you check at that point is a duplicate or not? Okay, so let's see. The list has 500 elements. Each element is in this range, okay? So the original list is not sorted. It has no structure for us to manipulate, okay? But if we create a copy of the list where now the elements are sorted, so then it has a structure. It has a pattern that we can manipulate. So we want to bypass this 5 million computational step. We don't want to go through the list again and again. We just want to go through it once. So what can we do so that we only go through the list once? So the idea is that we create some structure among these elements by sorting the elements, okay? So once we sort it, so these elements are not just randomly positioned in the list. They are sorted in either non-decreasing order or non-increasing order. And that kind of pattern allows us to manipulate it so that we can find out whether there is a duplicate very easily. So if X is a duplicate in particular, then all occurrence of X will be next to each other. Okay, so let's say, for example, this is my L, this is my list L. Okay, let's create this. So this is my list L, let's print L. Okay, as you can see, there is no structure. Okay, the duplicate can occur anywhere in the list. If we create some structure, we will see some kind of pattern that we can manipulate. So let's create, for example, L sorted equals to sorted L. Let's now print L sorted. This will create a new copy of the list where every element has been rearranged so that it's from lowest to highest. Okay, now the list sorted, the numbers are not randomly positioned. They are in a way that we can manipulate. We particularly know that the elements are from lowest to highest. Okay, so if there exists a duplicate, then these duplicated values must be next to each other. So if we go to the least ones, all right, just eyeballing it, you can easily find whether it has a duplicate or not by just looking. See, these two numbers appear next to each other. This is duplicated value, okay? And then you continue to search for it. And if you want to count how many such duplicated value, you basically just continue to look for any values that occur more than once next to each other. You don't have to search for far away because they are positioned in a way that if they are equal, they are next to each other, okay? So compared to this and here, we actually really don't know where is this duplicated value. This could be a duplicated value because it might occur somewhere afterwards or somewhere before afterwards that we don't know, okay? Then we have to go through it again, and then you check if it doesn't occur again, then you check this element, whether it occur one more time at the end, for example. And if it's not, then you're gonna have to check the subsequent elements. Does it occur one more time, and so on, because it's positioned randomly. But once it's sorted, we don't have to check for. This is not a duplicated value because there is no next element that is equal to this value. So we know for sure, we don't have to check for. This is not a duplicated value, this is not a duplicate value, and so on and so forth. And if you just keep on scrolling, you probably can find some duplicated value here and there. For example, here, this is definitely a duplicated value because next to it is a number that is equal to here, okay? So the idea is that if you have certain structure in the list that you are looking for, then it becomes easier. You don't have to look far for the duplicated values, okay? So that's what we're gonna do. So then you only look at the list once, okay? So here, my strategy, my search base is actually the sorted list. Okay, so I'm gonna look through elements in the list that has been sorted, okay? What are the properties of duplicates in the sorted list is that it is equal to the next value or equal to the previous value, okay? So if there is a, if the value is a duplicate value, it is equal to the previous or the next element, okay? So what happens when duplicate is found? We're just gonna output true and exit. Exit here means break, okay? Once we found, we don't look for any more. And when no duplicates are found after checking all the possibilities, after you go through every element in the sorted list and no possibilities is found, you just output false, okay? So basically, we're looking at the same thing as before. So we can just copy and paste the whole thing, except that we are doing it on the sorted list, okay? I'm gonna change here a little bit, okay? And our search phase, okay? So now for every value in the L sorted, okay? If, now here we're gonna be very careful here. If it's equal to the previous element, so we need a way to look at the previous elements, not just the current element. So for each of the elements that I'm currently examining, so I take one, I check the previous one. If it's not equals, I know this is not the one that I'm looking for. So I go to the next one, I pick it up and I check, is it equals to the previous one? If it's equal to the previous one, I found it. If it's not, I continue with the next element. So I need a way to go back to the previous element. And what we can do instead is, instead of checking, go through every element in the sorted list, I'm gonna go to the indices, okay? So for I in range of length of L sorted, okay, because index allow me to retrieve an element at a particular index, okay? So for I in range L sorted, so this will iterate through the indices of L sorted, okay, from 0 to length of L sorted -1 inclusive. Okay, these are all the indices, all right? So then I check if Li, this is the elements that I'm looking for at this moment. I'm gonna pick up the element at the I index of L. Is it equals to the previous element? Okay, if it's equals to the previous element, then I found the duplicate. Then house duplicate is equals to true, and I break. Once I found it, I stop, right? Okay, if it's not, Then I'm going to continue with my iterations. I go to the next elements and so on. However, let's look at this very carefully here. Okay, we start off with I equals to 0. For I in range length of L sorted, you start with I equals to 0. And so you pick up the element at the 0 index of L. And the 0 index of L is the first element. So we cannot compare it with the previous elements because there is no previous elements when you start off with the first element. So instead, I'm going to start off with 1, index 1. Okay, so I'm going to pick up the second element, which is the element at index 1, and I'm going to compare it with the first element. If it is the same, I found a duplicate. Has duplicate is equals to true now, I'm going to break it. Okay, I don't look for anymore, I stop. But if the second element, which is index 1, is not the same as the first element, which is index 0, okay, then I have to continue. So I will go to index 2. The next iteration will have index 2. That means the third element. From the third element, I check if it's equal to the second element. If it's equal, I found it. If it's not equal, I continue with I is equal to 3 and so on. Okay? So here I have everything. Here. So if has duplicate. So else print it exists duplicate in L. Okay, so let's run this. So it says that there exists duplicate in L, and if you want, you can also print out the value. Okay, so print which is, for example, Li in this case. Okay, so say 4088 occur once, more than once in the list. So you can also do a sanity check. Okay, how many times 4088 occurs in the list? Okay, they say it occur more 2 times, and hence 4088 is indeed a duplicate value. Okay, so here is an algorithm to check has duplicate. Okay, and what is the number of iterations? It only go through the list once. Okay, it's checked the same list once. If you compare to before in version 1, we check the same list 10,000 times. And version 2, on the other hand, only go through the list once. Okay, checking whether Li is equal to Li minus 1. This is considered insignificant computational step, negligible. So we don't count of it as a computational step. We only count how many times each element is being examined. Okay, so each element is being examined once. You go through the list exactly once only. So our analysis shows that the number of iterations is basically the length of L, which is 500, because the list has only 500 elements. So we only go through the list once. Okay, so in total, we examine only 500 elements. Okay, so if you compare with to before, okay, 500 versus this number of elements being checked, 5 million elements, 5 million of checking versus 500 times of checking. Okay, however, there's a thing here. So what do? Is that we go through, actually, I need to do this part here, L sorted, okay? L sorted here. So remember, it has to be L sorted. It's not L. L has no structure. L sorted has structure. So make sure this is L sorted. So this is a mistake, a big mistake, actually. Okay, let's do a sanity check, 3102. Let's see. Again. 3102. Actually, I need to run through it again. So let's do a sanity check on 3102 here very quickly. And because we know the L sorted is sorted, which means we can identify the positions very quickly. Because so the random integers here, every single time you run is different. So I just executed it once, so I have to execute this again. is now 643. So we look for 643 and just do a sanity check whether it occurs more than once. So here, and again, because I make a mistake here, it should be L sorted. Okay, so let's run this again. It's 398. So 398 indeed occur more than once. Okay, 398. Oh, and this is fine. Okay, so again, very careful here. In our version 2, every single thing that we run is on L sorted, it's not on L. Okay, otherwise the values that we get is wrong, it's incorrect computations. Okay, so again, once we have we always over L sorted. However, we are going through the sorted list. Okay, sorting itself, okay, is very computationally expensive. We incur a lot of computational steps. Okay, so think about it. If you were given a random list like this, how would you sort it? What is the algorithm that you want to do to sort it? What would you do to sort it? Okay, so for example, you know that for a sorted list, the minimum value has to be at the beginning, to be at the index 0. Okay, so you need to look for the minimum value in this random list here. And how do we find this minimum value? Okay, so the only way that you can do so similarly is to go through the list and check which one is the minimum. And then you look for the second minimum. To look for the second minimum, you also have to go through the list again to check what is the second minimum. Okay, there are better algorithms to do so, but this algorithm that I just mentioned is one way to sort the list from lowest to highest. But but from the way I describe it is that basically every single time to find the third minimum element, I have to go to the list again. To find the fourth minimum element, I have to go through the list again. So basically, it seems like I'm going through the list a lot of times. Okay, so we have some other efficient algorithms. Okay, so the most efficient algorithms for sorting, okay, will still incur at most n times log n computational step. We'll come back to this. What is log n here? This means logarithms. You should have learned this in high school. What is logarithms? This is logarithm base 2. Okay, means the highest power of 2 that is less than n. Okay, so when n is equals to 500, so when n is 500, so n will be our number of elements that we want to examine. In this case, our list has 500 elements. So then how many computation steps? So we're going to incur import.max. Okay, I want to compute what number of this computation step is. So if n equals to 500, I'm going to compute n times mat.log n. That would be 3107. So when equals to 500, it will incur 3107 computation steps if you are using the most efficient sorting algorithms to sort the list. Okay, so this is the amount that you incur when you sort the list, 3107 computational steps. So it's not just about 500, checking 500 elements. Before you go about checking these 500 elements, you have to sort the list first. This whole algorithm only works if you sort the list. Okay, it won't work if you don't have to sort the list to start off with. So you first have to sort the list, okay? And sorting a list will incur this number of computational steps. So in total, you incur 500 plus 3107 total computational step when n is equals to 500. So in total, when the list is 500 elements, okay, version 2 will incur 3107 plus, I need to do roughly here. Okay, this is just roughly speaking. 3107 plus 500 computational steps. Okay, so this is still better than 5 million computational steps in version 2, in version 1,